Good afternoon, guys. My name is Ahmed Qureshi, an associate professor. I lead additive manufacturing and design systems lab at the University of Alberta. So just a brief introduction about what's going to be in this presentation. We're going to talk about myself, my lab a little bit, how state of the things are in additive manufacturing in general, and I'm going to focus on a specific area, which is additive-subtractive polymer additive manufacturing systems, and I'll give you a couple of examples. And then in the end, we'll see what we're going to be doing next. So I founded Additive Design and Manufacturing Systems Laboratory at University of Alberta in 2015. And currently, I have around 30 people, including 6 postdocs, PhDs. And what we really do is carry out research with a focus on robotic, additive, and hybrid manufacturing systems. Now, in that case, the 4 areas that I really focus on are in development of manufacturing systems and processes, design for additive and hybrid manufacturing, implementing quality assurance and quality control systems, and of course, when you're doing additive manufacturing, materials is an integral part of additive manufacturing system. So a number of materials that we basically work on optimizing and making them ready for industry to uptake for additive manufacturing. So my lab's the only lab in Canada that houses under one roof a various amount of research-grade additive and hybrid manufacturing systems. So we have laser-directed energy deposition systems, powder bed fusion systems, wire arc additive manufacturing systems, plasma transfer arc additive manufacturing systems, and they're all open parameter research systems which we use to develop our parameters. In terms of polymers, in terms of materials, my research mostly spans metal additive manufacturing, and I'm not going to talk about that today. So I'll be mostly talking about polymers today, but in metals, we work with metals, ferrous and non-ferrous metals, high entropy alloys, rare earth alloyed metals, and in polymers, I work with homogeneous polymeric systems, thermoplastics, thermosets, as well as composite polymeric systems. And today, we'll focus our talk solely on thermoplastic with composites. In terms of quality, I believe in bidirectional digital twins. So this is a term that's widely abused nowadays. But in my opinion, digital twins are the ones which should be bidirectional and give you feedback, which many of the commercial systems do not allow. So hence why some of the systems that we have allow in situ sensing, in situ machine learning with hardware and material in the loop, and qualification. When we're talking about additive manufacturing, I'm a firm believer that printing what's been manufactured before through additive manufacturing is probably not a good strategy, unless nobody produces that and it's a legacy part and somebody's going to pay you top dollar for 3D printing that. If we want to realize the benefits of 3D printing, basically, you can generally divide them into 2 areas, one of which is assembly consolidation. So we combine multiple parts into a singular assembly, and the other one's function consolidation, in which you combine multiple functions into one thing. And so all of the additive manufacturing opportunities that you'll see would fall in one of those domains. It's either going to be assembly consolidation or function consolidation. I'll give you an example. This is a project that we did for a aftermarket car manufacturer. This is a BMW i3 intercooler, which we basically worked with topology optimization using TPMS lattice structures, and eventually we're able to reduce the weight by 30%, increase the temperature differential at a slight sacrifice to pressure increase, because you cannot optimize both. So with this comes the usability, that where do we want to use additive manufacturing. Now, one of the presenters talked about this before, and I'm going to take it up. So currently, my lab, as I was mentioning, we basically have in-house machines. So on the top right, you see a small-scale open parameter laser powder bed fusion for material development. On the left, we have a wire arc sensor fusion-based 8 degree of freedom robotic system developed in-house with digital twinning capability. On the bottom left, we have a laser-directed energy deposition hybrid manufacturing system for ferrous and non-ferrous metals. And on the right, a plasma transfer arc source that can do hybrid manufacturing with sensor fusion. In terms of polymers, we apply the same. So 2 areas that we work on is fused granular fabrication composite robotic 3D printing using robotic systems and doing in situ machining. So what you're seeing on the right side is a polymer part that has been 3D printing, and we just bring it back to the spec by machining. On the left, we use a similar part for doing investment costing. Now, if you look at the 3D printing process, it is absolutely broken. I don't have a better word for it. So you first do a CAD model with any CAD modeling software of your choice, which you should not be using normally because most of the CAD models are boundary representation solid models and are not set or usable for free-form organic fabrications. Then we basically do CAM in a bunch of separate softwares. Then we do simulation in a bunch of other softwares. And then we do fabrication. Then we do post-processing, removing supports, and eventually verification. So it is a disjointed process that involves an engineer to be an expert at multiple different softwares. So the main points on the CAD, we cannot really do with the standard CAD tools, we cannot really do free-form, organic, topologically driven, function-based design. There's no software. There are new softwares coming in, Topology or Gen 3D are some of that example. In terms of CAM, 3D printing processes came up from a 2.5 degree of freedom heritage. So they don't really do 3-axis very well. So there is a strong need, if we want to make them competitive, there is a strong need to make them 5-axis, 6-axis, ideally 8-axis. In terms of simulation, we just have to make a number of many jumps of faith and assumptions to fine-tune our simulation to what's happening in real life. And if we have to do that, we got to think about there's something broken in the loop where we need to have an iterative link between the process and the FEA. On the fabrication, powder bed fusion is very famous. However, it's not really scalable beyond a meter scale. But what if we're printing at 3 meters, 4 meters? What do? There's not much capability in situ sensing. And then, support structures is everybody's nightmare. So, if you've ever printed a serious part in metal and thought about how you're going to EDM it and how much time it's going to take, this should have been done before you printed the part. So, thinking that beforehand is important. And in terms of verification, we've had some really good presentations earlier in the day that talked about that, so I'm not going to talk about that, right? So if I look at it and if I narrow my focus on today's talk, so some of the things that are really challenging is to assure in situ geometric conformance for path planning, for quality assurance, for quality control. Taking care of anisotropy. Anisotropy is very important in metals and in polymers and is one of the limitations of additive manufacturing. Final geometric finish, so stair-stepping that comes up, and things like overhangs. So how do we deal with that? I wish I had hours with you, which I don't, and the rest of the 11 minutes that I have, I'm just going to show you 2 examples out of many things that we do. So I'm going to today talk about in-the-loop metrology for additive manufacturing, and I'm going to talk to you about interwoven 3D printing. So polymer composite is an important part of today's industry. A simple example is that one of the most popular airliner of today, Boeing 787 Dreamliner, is 50% composites. Many performance parts in the cars are on carbon fiber composites. However, carbon fiber composite is a very, very slow process in which we do pre-preg, we take the carbon fiber cloth and we lay it up, and then we do autoclaving or curing to get the part that we want. It is slow, it is difficult, it needs a lot of tooling to get one part, and if you have to change the part, you have to do the tooling again. And thirdly, you cannot switch over from one part to another, so there's very less operational and manufacturing flexibility. My questions are what are the barriers of bringing 3D printing at par with composite manufacturing, which it is not? Which tools will disrupt the 3D printing industry for making sure that we are able to come at par with what the carbon fiber polymer reinforced plastic industry is doing? So what we really did was looked at what people are doing. So people have been doing a bunch of things. So doing non-planar layers, doing some kind of zigzag pattern layers, or doing layers with intermittent materials in them. All of them do not care of the anisotropy in polymers. The anisotropy remains. So we came up with two very novel algorithms. One of this algorithm that's called Z-stitch algorithm, it allows a designer to implement a interwoven stitch in a polymer composite. It's the first declaration of any such algorithm. This has been applied for a US patent. It's patent pending. So what's happening? I'll let you see what's happening. So what happens is rather than printing in layers, we print in 3-axis right now. And in the 3-axis, we are basically printing different layers asynchronously. The algorithm determines what needs to be printed when, and you can see stitches happening in the print. And as the stitches happen in the print, the part print moves on, eventually leaving us with a part that is actually stitched across the z-axis. What we want to do, what we want to use this is for carbon fiber reinforced polymer interwoven 3D printing. So at the end of the day, what comes up is a very complex composite part, which is linked not only in X, Y, and Z direction, but also in the Z direction. X and Y direction, but also in the Z direction. This is a CT scan of that 3D printed part. We use CT extensively for understanding what we're doing. So on the top right, you can see the actual print. On the this side, what you're seeing is the CT scan as it moves in the direction given by the blue arrow. And so you can see that the stitch is going in X, Y, and Z direction as a function of the part. It's all nice and fancy and yet another algorithm. Let's put it to the test. The green line that you see is the Z-stitch algorithm. So this test case is a 60% infill. So we have tested this with the best possible combination that you can get on a 60% infill part, which is a axially oriented fibers, but we've also done 45 degrees and 45 degrees. One thing you'll notice is that this is quasi-isotropic. So although the red and blue, which are the other algorithms, they vary between 40 megapascals all the way down to around 18 megapascals, our print stays nominally at all the things. So imagine the advantages it has, that if you're defining a metamaterial tensor, stiffness tensor in Abacus or in ANSYS, then you don't have to do complex metamaterial definitions. The second thing is our algorithm at 60% specific infill outperforms the 60% normal infill by a big margin. So we are 20–30% more effective. So that was one part. What about the next thing? So I'm going to talk about metrology. I'm going to talk about conformance. How do we do that? On smaller parts, we can put parts on a CT, as one of the speakers was showing a very nice graph. So, we have different metrological ways to assess the solidification, assess the porosity, assess the dimensional conformance. But as your parts start becoming larger and larger and larger, CT is no longer an option. How many different parts or how many different samples can you pick up for an SEM or a microscopic analysis on a 3-meter build? So what we wanted to then do was to understand that if there is a common digital tool chain which we can use to assess the metrology and other properties. So we have an in-house software ecosystem that does CAM, that does in-situ sensing, that does machine learning in hardware. I don't have time to talk about all that, so I'm going to focus simply right now on geometric aspects. So this is a software that we've commercialized based on the research out of our lab. And this combines all of the hybrid manufacturing processes in one go. So you can see a damaged propeller which has top. So now this is all being done in a singular software environment. You look at a software, you look at the damage, you compare it to a nominal part, you basically get the damage right there. Once you get the damage, you cannot directly 3D print the damage because it's damaged. So you need to use subtractive operations on it. So our software, the algorithms, they have tool definitions in it, and using that tool, it can compute the subtractive surfaces which need to be done on a part, and from there, what happens next is that you then define the additive manufacturing part. So once all of that happens, you have your part. But when you do additive manufacturing, it's you get very poor compliance in case of a CNC. So this is the test run. So you can see that damaged propeller there, which is being prepared for through subtractive. Now we're doing laser DED on that. And as you see that when we do the laser deposition on that, this is going to go all over the place because you cannot get 50 micron surface finish from subtractive manufacturing. So the same software also tells the machine how to finish it up, all under one ecosystem, all under one go, which would have otherwise needed you to have at least 4 or 5 different softwares. This is the final part. The porosity in this part was better than the cast porosity of the part which it was, right? So let's go on and look at something else. So in this specific video, can you please help me play this video? So what we're doing is we're basically doing hybrid manufacturing for rapid investment casting. Some of our work is around rapid investment casting. So again, using the same software that we had developed before, we have a hybrid manufacturing system that can deposit fused granulated fusion, so pellet-based deposition of a wax, which you can machine, and then you can deposit in the same ecosystem the mold material, which you can use for investment casting. So you can also do the metrology later on using the same ecosystem. So you can see that here's this wax being printed for this is an ASME 16.5 flange that our industrial partner sometimes uses, and it uses a very specific material. So you can see that basically, you'll see in a minute flange being printed. And then in the same place, without removing the part, that same part is finished to the CNC finish. The finish that we have on this is final net finish that we want. And you can do any other features in there right there and then, right? And one thing you will not see in this is that on top of that, we have another extruder, which is for using a specific type of investment casting plaster that then puts plaster on it. You can do the before and after analysis of the geometric conformance, and with that, you can get the part done in one go, take the mold off, bake it, cast it, and be done with it. So looking ahead, what are we doing now? Now that we have all of these things in place, what we are looking now is we're looking very large scale. So we, over years, have developed partnerships with different OEMs, which allow us to do systems at scale. So you could do a bunch of things with them. For example, online metrological assurance on the scale of vehicles, boats, planes, looking at different hybrid manufacturing operations. So for example, if somebody wants to repair a wall on a container, so with the robotic system integrated and the software ecosystem that we've developed, you could basically see what needs to be done, automatically assess damages, and do 3D printing, sandblasting, painting, metrology. The sky's the limit. So with that, thank you very much for your time and your attention.
This is for you. Thank you very much, Dr. Qureshi, for your presentation. We're going to start the Q&A session. Any question for Dr. Qureshi? Yes, Dr. Alex, yes.
Thank you for your presentation. I really enjoy it. I have a curiosity regarding to your polymeric materials, the new way you are thinking to replace, for instance, carbon fiber and so on. So I'm just wondering regarding the properties. I noticed that, for instance, you have a curve that is quite similar to metals, but it's a polymeric material. And of course, deformation induced crystallinity and other effects. Just wondering, not to go into the details, how did you manage to address the addition problem, the bonding between different polymeric materials, because it is very important to make sure that there is really bonded.
So Alex, you're talking about bonding between different materials? So that's actually a really, really good question. And as we know that additive manufacturing is a wicked field. So you solve one problem and there are another. So right now, this is what we are doing. So the first effort was on breaking the barrier of 2.5D fiber-based 3D printing, which we just broke. Now that we've broken it, now we are looking at what are the interfacial bonding conditions between the carbon fiber and the polymer. So we are using polyethyl ether ketone right now because it has aerospace applications. So there are the bigger challenges that I see. The intermatrix adhesion is not a problem. So we have tested things enough in-house to understand that our peak adhesion between the layers, it is very good. The problem that we really have right now is the adhesion and the porosity between the carbon fiber, and the matrix, right? And we have a strategy to address that. So I didn't have time to talk about this, but with the same machine, we have developed a very interesting and novel ultrasonic consolidation system. So that, and I was very happy when I saw that, the lab here also has an ultrasonic consolidation-based micro injection molding system. So our approach is similar to that, but it's inline. So what really happens is that as the material is being printed, ultrasonic consolidation happens just behind to ensure that if there are any voids, they can be collapsed. This is work in progress, though.
Just a final remark from my side. Porosity in polymeric materials, it is not always a bad issue. It can help you to even enhance the physical properties. It's just a matter of taking a look. So we will talk later. Okay?
Absolutely.
Thank you very much.
Absolutely.
Thank you.